Welcome to ArgMax, a show about machine learning where we talk about recent research in machine learning and we decipher papers, ask the hard questions, and just satisfy our curiosity. My name is Taka Hasegawa.
I'm Vahe Hagopian.
And Farouk Rahman.
Welcome to this second episode on our reboot with video of research papers. We are today covering Hindsight Experience Replay by Andrzej Czechowicz et al. From OpenAI. This paper was published back in 2018, but there's some renewed interest in goal-conditioned reinforcement learning, and this is pretty prominent paper in that area, so we decided to give it a read and discuss it on this podcast slash YouTube video. Vahe, do you want to give us a quick introduction about this paper?
Yeah, so with goal conditioned reinforcement learning, instead of only having a state space, we also have a goal space. So we can condition our action based on what state we're in and what goal we're trying to achieve. Typically, when we do reinforcement learning, we have one goal in mind, like a primary task. But it's possible to, even if that's your original goal, it's possible to, or that's the original intent, it's possible to add multiple goals, secondary goals, and design reward functions for each of them. And in this paper, it's kind of modeled after DQN, Deep Q Networks, which was a paper from 2015. It's a very kind of fundamental algorithm used in off-policy reinforcement learning. But the idea is, normally, when the agent takes a trajectory during an episode, if it fails to, especially if we have sparse rewards, if it fails to achieve its objective, we don't really learn much because we didn't get any reward. And typically the way engineers manage this is they add some kind of reward shaping. So reward shaping is something where you create rewards that maybe weren't part of the original task, but to kind of nudge your agent to learn. So you might, for instance, think about sub goals in the environment, or things that if your agent achieves, takes him part of the way to the actual ultimate objective. Reward shaping can be very difficult. It's often fraught with peril because you may incentivize behaviors that you weren't expecting, or aren't really, things you want the agent to do. So in this paper, they kind of abandon reward shaping and use this new method where they store all trajectories that the agent experiences during episodes in a replay buffer, similar to DQN. But they define multiple goals, including ones that maybe would have been viewed, or definitely would have been viewed, as failures in the original task. And the idea is that even if an agent doesn't achieve what you really wanted to achieve, if it achieves one of these other goals, and you're actually sample that goal as something you want to learn. Let's say an agent experiences a particular trajectory during an episode, and it achieves one of these other goals that you've defined for this task that isn't one of the original goals. You can still do gradient descent because it actually got a reward for this other new goal that you defined. And so you can learn something about the environment, even though it didn't achieve the original goal. So if you have a bunch of these goals that you've defined, you've kind of turned the original sparse reward into a dense reward, but not by reward shaping, by just having tons of goals that all yield some kind of reward. And what they found is that if you do this, similar to reward shaping, you actually having success with all these other goals correlates with having success with the primary goal. So yeah, I guess that's enough of a summary.
Nice. The thing that I like about kind of zooming out to the macro view of just goal condition reinforcement learning in general is I feel like in a lot of cases, especially more kind of real life scenarios or robotic scenarios, where the goal isn't clear, right? Like, with games like Go or racing or whatnot, Grid World, the goals are pretty clear. Like, you want to get to the goal, you want to beat the opponent. But with more nuanced tasks, like robotics or even language, I feel like it's hard to define that one goal. And I feel like this kind of research will play into that kind of challenge of like, and we talked about this briefly when we talked about InstructGPT, where we said, like, they have the reward model and they rank the responses by certain different dimensions, right? Of is this hallucinating, is this toxic, is this helpful? But the graders were all, or the labelers were all kind of beholden to just one ranking. Like, they couldn't say, okay, if I just take into perspective honesty, this is going to be the rank. If I just look at helpfulness, like, this is going to be the rank. They couldn't do that. But with this stuff, it feels a little bit more natural to take into account multiple goals. So just kind of my random thoughts there. But let's go back to the algorithm that you described. So my little doodle here is the my understanding. So replay buffer, we all know from DQN, is the place where we store the experiences of the agent. If we just store the experiences as is, that's the same as vanilla DQN. But what you're saying, Vahe, is this world has multiple goals. So even if your agent is acting according to the original goals, that experience we can apply to the different goals as well, and kind of multiply the amount of experience we get based on those different goals.
Yeah, go ahead.
My understanding here is, like, this is, so it feels a little bit similar to DynaQ, where, like, it's model based. DynaQ, like, tries to build a model, and with one experience they try to kind of use their own model to come up with different rewards. But my understanding is this is a little bit different from Dyna, in that it's not learning a model. It's still reliant on the environment to give us that reward signal. So when we say that we can get experiences from these different goals, we're still querying the environment, right? So we say, we got this experience for goal 1. What if we swap out the goal? What do you say, environment? What would be my reward? So we're actually talking to the environment multiple times, right?
Yeah, I probably should have been more clear with the actual reward structure. This methodology is geared toward very, very sparse rewards. So specifically, like, binary sparse. So imagine the original task only had one goal. Like, they give an example which I kind of like, which is imagine you're playing hockey and you have only one goal, and that is to get the puck into the net, and you get a +1 reward if you do that, and you get 0 no matter what otherwise, right? That's a task-oriented, very clear task, right? You have to score a goal, and there's only one reward, a +1 if you do, and 0 otherwise. You can define other goals, which are basically, you can imagine there's other nets everywhere along maybe that particular line where the actual net is. So if the player actually sends the puck anywhere along that line, he scores some goal with respect to some imaginary net where that puck would have entered, right? So you can imagine, like, instead of one goal, maybe have 10 goals stretching the entire length of the ice. But you would still make the reward binary. So you have to define reward functions, but they're very easy. It's just +1. All you're doing is shifting the net by all along that line. And so now every time you run an episode, you pull an episode from this replay buffer, if you also pull a goal, you also pull like a particular goal. So like if you pull goal G2, which is where the puck actually went because you missed the main goal, you're still scoring with respect to this goal G2. And so you're actually getting a +1. You're not just getting a 0 all the time.
Yeah, I guess another way to maybe rephrase it might be the ability to shoot the puck even off target is progress towards shooting it on target.
Yeah, exactly.
Right. So the failures to score, you were still able to like shoot the puck or ball or whatever in this example. So really, it's okay, you failed, but you need to kind of retarget, you need to correct where you're firing it, right? But that ability, that sub goal of the ability to just shoot the puck is progress.
Yeah, so the way I understand it, and correct me if I'm wrong, let's say we have a neural network that's storing the value function, right? We have a new input to this. Usually we have the state of the environment as an input, like the state features, the features of the state as an input to the neural network. We additionally add the goal as an input now. And what we're doing is when you shoot the puck off target, like Farouk said, but score a goal in this other imaginary net, we're actually providing this alternate goal as an input. So the neural network knows that whatever happened, this trajectory is not relative to the original goal because it has the goal as an input. However, the same parameters that affect the original goal are there and are being updated by gradient descent. So I guess the idea is that when you succeed at one of these many alternate goals, you're potentially still moving the parameters in the right direction, even for the original goal. And I think that's kind of the essence of why this is successful. Whereas if we didn't have these alternate tasks, we would just have a 0 reward, right? We'd never have any rewards for missing the actual net.
So I think something you mentioned, Bahe, earlier is like the motivation for this is to solve sparse reward environments, right? Where it might be you need to make significant progress until you even see a reward. So
they say it's kind of like curriculum learning.
Yeah. So if you only ever get a reward if you score in a net, in the goal, you might never see that, right? And by creating kind of this a second goal of you are rewarded for shooting in this imaginary net, you can propagate that signal earlier so that you kind of make progress. So really it's a way of rewarding for failure.
Yeah, and actually to your point, Farouk, I think Taka, if you scroll down maybe a little bit, they have the second example here, I think in 2.1. Oh no, it's not here, sorry. They have another example here somewhere where they define this task where you have this bit string. Oh, there it is. Bit flipping, section 3.1. You have this bit string, and if you use regular RL, it's been shown that it's like impossible to solve if the bit string is longer than 10 bits. So there's this particular task where you have to find this particular pattern of bits, and there's just the state space is too big. There's too much to explore. But with goal conditioned RL, I think they were able to do up to like 50 bits. So it was like an example of how powerful it is in these sparse reward environments.
So I guess on the topic of the sparse environment, a competing method might be reward shaping, right? So
It is. Yeah.
why not do reward shaping?
That's a great question. I think you can do reward shaping. I mean, that's the norm, and I think most people today still do reward shaping, right? So clearly that works too. Their argument is that it's harder, and they give a couple examples of very complicated reward functions. And I think they're saying, hey, there are environments where it's much easier to do what we're doing, to just define multiple goals and have very simple binary rewards for each of these goals.
Yeah, and
Now-
reward shaping requires domain knowledge, whereas I guess this multi-goal thing, if you want to treat it similar to reward shaping, it might need like for example, that hockey example, I can see that as kind of a reward shaping-esque kind of direction, right? Like you're wanting to teach the agent to shoot the puck in a forward direction, and that's why you have like goals that are kind of spanning the opponent's side of the court.
Which requires a little domain knowledge, right? Because you
require
have to know
domain
where to
knowledge.
put the goals. Yeah.
Yeah, but like in
I
like a robotics world where you really do have multiple tasks that you want the robot to acquire, it does feel like this is a more natural fit compared to reward shaping.
I think, yeah, I agree. I think in a task where there are multiple behaviors that you deem useful, I think this fits very well. But I agree with Farouk. Like, I can think of tasks where the agent can do many things and they're all undesirable except for like one thing. I feel like it might be hard to fit this framework into that kind of an environment. Like one example is like, the lunar lander environment where you're trying to land a craft onto the moon, and success is landing it in the correct orientation with very slow speed on the landing pad. It's like a very precise set of things have to happen, and the lander is capable of accelerating in any direction, rotating, moving anywhere. And it's not easy for me to naturally define alternate goals in that environment. Whereas I can see for like a robotics environment, I can barely, if a goal of a robot is if your goal is to have it pick up a block and put it on a particular spot in the room, I can think of many, many other goals that kind of correlate with that, which is maybe picking up the block and putting it somewhere else in the room, or pushing the block, or these are all kind of useful skills for the robot to have. Whereas a lander just flying out of control and crashing is not really a useful skill. So I also agree. I wonder if maybe for some environments, some tasks, reward shaping might be a more natural fit, and for others, this framework of creating multiple goals might be a more natural fit.
So maybe let's talk about the algorithm a little bit more in detail.
Yeah, we can get back to the reward shaping.
So
hindsight
the
experience.
idea behind her is you experience some episode where you start at an initial state, end at a terminating state, and you store in the replay buffer every transition, not only with the original goal, but also with a subset of the other goals. Okay. So it's like if you're having, I mean, if you're having like n experiences with regular DQN, basically you're going to end up with G times n, where G is the number of goals experiences in the replay buffer. I mean, the size of the buffer is probably going to be the same, so it's not necessarily that the replay buffer is bigger, but the velocity at which the replay buffer gets filled is G times faster. One choice they made with her is the additional set of goals used for replay. Simplest version, we replay each trajectory with the goal which is achieved in the final state of the episode. Okay, so this is the algorithm. Looks very similar to DQN, where you have a replay buffer and you store that replay buffer. You store the experiences in the replay buffer. But so yeah, they're pretty clear with that too, right? They say here this is standard experience replay, and this is the part where her comes into play. So starting from the beginning, for each episode, you're going to sample a goal and an initial state. So there's one goal and one initial state that you sampled. And then for the length of that episode, you're going to sample from the behavior policy. So you're acting as if, this goal G is the only goal, right? Because this policy, behavior policy, is given this goal. And so you're acting inside the environment as if this G, the original goal, is the only goal. And then you keep executing action, and then you go into the next state. And that gets you to the end of the episode. So this is one episode, right? And then once you experience that episode, what you do is, this is standard experience replay, where you just store that experience, each of those experiences, into your replay buffer. But this part is basically where Hindsight Experience Replay does its thing. It loops over all of the different goals, which they denote as G dash, and they get a reward for each state action pair from this episode that they just experienced, given that the goal is that different goal. And then, so yeah, this brings me back to my original point, where like this part felt like Dyna to me, where like you're doing some kind of simulation, but it's not really a simulation in that it's actually querying the environment with this state action pair and goal tuple, and then you're getting an actual reward, and then you're storing that transition in the replay buffer, and then you just
Yeah, it's creating additional transitions from each of the transitions acquired during that previous episode.
Yeah,
it's just like multiplying.
So effectively, you're saying if my goal were to, to pick in place, or to push, or to slide, I guess, what would my behavior policy have rewarded me with? Or no, sorry, what would my I guess environment have rewarded me? Yeah, have rewarded me
with the original behavior policy,
with the original, yeah,
which is kind of wonky. Like, if it feels like if those goals are separate enough, and then if you kind of learn enough, like each behavior policy, I feel like, will diverge, right? So like let's say the goals are push, pick, and slide, right? As the agent gets better on each of those behaviors, the amount that you learn from the other goals will diminish, right? Because like those are the behaviors and goals don't match.
That might be okay though, because the goal is an input to the neural network that's storing these values. So for example, right, like you can think of the neural network now, to your point, as encompassing the values of a bunch of different tasks. So maybe you need a larger neural network, right? Potentially, but even if they diverge, that's okay, because they're conditioned on the goal as an input feature.
Yeah.
And there's probably still some things to be shared, right?
I think it depends on how much shared positive like correlation there is between.
But I don't think it can really hurt you, as long as you're conditioning on the goal as a feature. Or I can see how it doesn't hurt much to have like divergent tasks.
Yeah, it would be curious to see if you had completely divergent tasks, because in all the examples, the failure is progress towards the goal. If the failure is
Not progress, like against the goal,
if it
like
no
going
even
against the goal.
even anti-correlation is shared features, right? Like
Sure,
like because
sure.
it's like the negative. But if it's like random, right? If there's like, you know, if one task,
You could probably design some pathological task to like try to
yeah,
stymie this algorithm,
yeah.
but
Because
I don't know.
because if you think about it, let's say you're given a state, like you're in a state where you have picked up the block. Let's just say you've picked up the block, right? This is the I guess the state action pair is you've now grasped this block, right? That maybe the action was to like close the grippers or something like that. Well, conditioned on that, and each of your goals, if you want to slide, in order to slide the block, you might slide towards your target, right? If you want to push the block, it's the same thing, because you're pushing, it's the same kind of next action. Versus if you want to pick and place the block, it's kind of a similar thing. You could either slide it, you could like move it back, or something like that. So given that state action pair of having the block in your graspers and like compressing it or something, as that action, all the next actions you might take are kind of correlated, right? They're kind of similar. So I guess in this example, and in the task they demonstrate, it feels like a good fit. But yeah, as Vi said, I think we could come up with some, not even anti-correlated, but some like completely random, but even in that case, maybe it doesn't hurt.
Yeah, I don't think
Yeah.
I don't think it's really a big deal.
Yeah,
I agree. And maybe it's a different form of exploration, right? If the goal is A, but you're rewarded with respect to a different goal, maybe that's kind of a different form of exploration. Like it's like sub goal directed exploration or something. I feel
Sure.
like there might be some kind of
Sure.
exploration thing in there too. The other thing I thought while looking at this was probably the replay buffer needs to be bigger compared to like a vanilla DQN thing, right? Because you're going to fill up with experiences pretty quickly if you're
You have a
thinking
lot of
about
goals.
different if you're thinking about different goals. So that tells me that at least the buffer size needs to be goal times bigger.
Yeah, it makes sense because typically, like, at least from my experience when designing buffer sizes, you want to have a happy medium of enough memories so that you have diversity, but not so much that you're sampling from behavior that's completely different than the current policy, right?
So
like,
I think
you want the
that's
policy to be relatively like time invariant.
so if the goals are correlated, then it might not need to be G times bigger, because like I think you could, in the naive case, I think it makes sense. I think I see where you're coming from, where it would need to be significantly larger. But for example, if your original task was pick and place, and you only got one reward for that, and it was this really sparse reward, just a 1 or 0 for pick and place, you'd be getting nothing from sliding. But that's initially what the model would, or what the policy would start with, right? It would try to pick and place. It would slide it by accident. It would push it by accident, because it doesn't have that fine control yet. Like the policy can't control it. But because you've explicitly defined some of those as goals, it that would help. Like that would kind of make progress towards the goal. So if I guess if you did reward shaping, and you had a certain size buffer, and you did her and you got a certain size buffer, I think the point here is that you can't even solve this problem if you didn't do any of those two things, right? So having a larger, I guess, having a larger buffer size, I think is like almost an inconsequential like argument, right? Because you can't even solve the problem without it. But even if you want to make that argument, because some of these sub goals are positively correlated, some of those experiences, even if you could have solved the problem without those two things, would already exist in that like distribution already. Vahe, I think you're muted.
I don't think you can really lose by going G times back. You just might not need to, I think is what you're saying. But like if you multiplied a DQN buffer size by G, you're going to kind of get the same horizons worth of trajectories in terms of horizon in the sense of how old the policy that you're sampling is. But what you're saying is you may not need to go that deep.
Correct.
Yeah.
Interesting. Yeah, your mentioning of correlations kind of reminds me of the DQM paper where like the whole point of experience replay was they wanted to break the correlations between the experiences, right? But now we're having essentially very similar looking experience tuples that are inside the replay buffer now, right? So if we're saying that if
they're
goals
not, if the goals are correlated, remember the reward for some of those goals is not one, or it's not going to be one.
Oh, the tuple is going to be different, right?
The tuple is different, yeah.
That's a good point. Yep, makes sense.
But what do you mean? Aren't the rewards always 1 or 0?
They're 1 or 0, but for example, let's say you're doing pick and place and you fail to pick and place, but you slide it. For the slide goal, the reward's 1, but for the other task, it's 0.
Yeah, you're gonna get a 0 if that's
right
goal
so,
you're currently.
So basically, like from your distribution, you're kind of giving it the signal that, hey, this is somewhat a condition on this particular goal. This is where the direction I want to go in, but I'm still not there at this other goal, right? So it's kind of like an average, I guess, over
But the cool thing is like you're getting like G times as many transitions out of 1, right? So I can see why this would be a very sample efficient algorithm, right? You're kind of extracting more signal out of each trajectory than you would normally if you were doing regular reinforcement learning.
Because when you look at the 3 tasks, pick and place is the obvious, most difficult task there. Sliding and pushing are easier tasks. So in order to do that pick and place, you're going to have a lot of zeros. So what you're doing by adding these additional goals of slide and push is you're saying, okay, if I fail to pick and place, but I do the slide, I'm going to reward you. So you push you in that direction. That this is a behavior it's
a curriculum learning thing. They mentioned that it's basically like you're rewarding the agent for doing simpler tasks on the road to doing the
harder task. Yeah. Right.
Makes sense.
Oh, here's some results.
Does HCR improve performance? We evaluate DDPG with and without her on all 3 tasks. So DDPG plus her is the red line. So we're seeing that pushing and sliding, definitely her is outperforming everything else.
So there's actually two DDPG plus hers, the blue and the red.
Oh, it's the
I
blue
think
and the red.
the red involves a different type of strategy of goal creation, maybe.
Yeah. So if you look here, based DDPG and using the count-based exploration based on like state counts, it can't even solve two of the tasks.
More like most of the tasks.
Yeah.
Well, yeah. I mean,
Well,
to be
sliding
fair,
it's able to do a little bit.
sliding. Oh yeah,
20%.
the green one. Yep.
I'm surprised that it's not even able to do the baselines are not even able to do pushing. It's pretty surprising that.
I mean, if you look at the number of epochs, it's 200 on the x-axis. This is a little bit apples to oranges, or it's like apples to bushels of apples, right? Because like vanilla DDPG or DDPG plus count-based exploration is only dealing with one experience per episode, or the number of transitions per episode, whereas her, you're kind of multiplying by 3, right? Like you're getting more experience.
That's actually a good point, I think. Like it, like if you have a sample efficient algorithm, of course it's going to learn faster, but that doesn't mean the other algorithm won't also learn. It just might learn more slowly. I guess their point is that, hey, I mean, I agree with you. Like if they had another graph showing that, DDPG plus count-based exploration also succeeds at solving this environment, it just takes maybe 4 times as many epochs.
So effectively, we're saying that the x-axis needs to be longer.
Yep,
kind of, because I think
to be longer.
That tells us. I mean, if their goal is to just show that in a certain amount of time, this algorithm is better, but a lot of people don't care about the time. Like they want to know if that environment can even be solved, right? And these graphs are kind of misleading, I think, is kind of what Taka's saying. In that sense, if you don't look closely, you might think, hey, regular DDPG can't even solve the environment, but that may not be true because it's less sample efficient. So it might have, if we ran it longer, it might have been fine. Right?
It might have, but I think we would need to know the context of this task. Like it says 200 epochs. Is that what is that in the context of this of these tasks? Is that a long time? Is that
well, I guess to put it another way, these algorithms are just barely solving it in 200 epochs. Like they're converging right around 150, 200. So obviously something that's far less sample efficient, there's no way they're going to converge in that time, right? So to give them a fair shot, you have to go a couple multiples out, and they don't do that.
I think for pick and place they do that. I think pick and place.
Yeah, I agree. You're right about that. It seems like there's a couple more multiples there.
Yeah.
So that's a good counterexample to what I said. Like, it's not DDPG is not learning pick and place, at least in 4x the time, right?
Yeah, but for sure, the her stuff is outperforming. So
yeah,
that is being shown here.
Well, yeah, outperforming, it's more sample efficient as well.
So yeah, the sample. So okay, let me. So sample efficient to me is like you're dealing with the same number of samples, but you're learning more efficiently, right? So like you have 100 things in your training set, and you're utilizing those 100 things much more better.
You're getting more of the signal out of them.
So yeah, my whole thing was you have more samples. Like the her stuff is ending up with 300 samples, whereas vanilla DDPG is only ending up with 100 samples. So it's hard to tell sample efficiency from this chart because the number of because you're actually querying the environment times G times more times, right? So
wait,
it's
wait,
like,
wait. Are you? You're both algorithms are running the same number of episodes through the actual environment, right?
right, but with her, you're querying for all the other goals as well.
Only within your algorithm, though. You're not querying the environment with the
You
other
have to
goals.
query the environment in order to get the actual reward. Like you can't, because this is not model-based learning. So you don't have a model of the environment
I
inside.
think in the I think I was gonna disagree with you initially, Taka, but based off that last part, I think I see what you're saying. If you go back up to the algorithm, it is actually, it seems like you do have to query the environment. So like in that second for loop, not the like the inner one where you're looping over each goal,
Yeah.
that seems like you're querying the environment for the reward.
You
You're
have
not.
to.
No, you're not. You're not. You're
No?
not. No.
You have to, because otherwise, how would you know the reward?
Oh, I thought that was your own reward function. That's your own.
We don't have a reward function, right?
So scroll up to the given right at the top of the algorithm. You're given a reward function R from S cross A cross G to the real numbers. I believe that's your reward function. You have to define that based on all the goals, all the different goals, and it's going to be the environment.
But who is you? You is not the agent, right? You
Mm-hmm.
is the environment.
No, you is the person designing the agent, the engineer. So the environment is out of your control. You're not allowed to touch the environment.
Right, and the reward is part of the environment.
It's giving you one reward for one task,
Mm-hmm.
one binary reward. Now you're going to put a wrapper around that. When the goal is the original goal, you're just going to use the environment's reward. But when it's one of the other goals that you've defined as the engineer, the wrapper is going to assign ones in all sorts of different spots based on whatever that goal is. Now, just to make sure that I'm not just making this up, maybe we can scroll up and actually look for where they define the reward function, because that's the way I understood it, but I could be wrong.
So how do you define the reward function?
But while we're looking for that, Farouk, my understanding was that no matter what algorithm, whether you're using her or not her, you're only querying the environment once. And then you're doing these next two for loops in the algorithm all inside of the agent's code. Like you're creating a whole bunch of trajectories based on.
I actually think you're right. You only sample an action once.
Yeah. So it really is. I mean, the sample efficiency really is a thing here.
Let's see. Yeah. I guess I could buy that. So but like that goes against the whole model-free learning stuff, because if you're really model-free, how can you define a reward function on your own? Like
well, I mean, they do that in reward shaping, and that's model-free too, right? When you do reward shaping, the only difference between this reward and actual reward shaping is this one's very simple. It's just a +1. It's just a binary 1 assigned to every single goal that you define. So it's like a very simple form of reward shaping.
Okay. So then this stuff looks starting to look really similar to reward shaping then. Yeah, if that's the case.
Effectively, is this like a more general case of just reward shaping, where you're taking some other state and you're just making it a 1?
You know, I wouldn't be surprised if underlying all of this, some theorist shows that it's equivalent to reward shaping. But I, like that deep down underneath, maybe there's some equivalence. But I can see how.
I'm not saying that it's, because the thing with reward shaping often is like you have a gradient, or like you have this more like linearly spaced, or some sort of, you have something clever that's based on like the inverse distance, or like the distance to the target, or things like that, where it's kind of progressive. Here, it's not progressive. It's still binary. It's just that.
Yeah, but you're adding
you're
complexity
taking
with the tasks. You're shifting the complexity from complexity of reward to complexity of tasks, of goals.
right. So instead of having to define, I mean, I guess in some cases it's less domain knowledge, because you don't have to define this, this this like clever reward shaping kind of heuristic, or something like that, where you need to know something about what the optimal solution looks like.
But you have to define these states where the goal
But you have
terminates.
to define these
Where the task
states.
terminates.
Yeah, where it's like you're like, okay, I need to pick and place, and the mistakes that I might make on the way to picking and placing are things like pushing and sliding, right? Versus and those might be relevant tasks that you care about, right? You might want to slide at some point, with a robotic hand, versus having to solve picking and placing by trying to come up with this like reward shaping. So I can see why. I think they have a little section on it we can talk about in a little bit, but I think we want to get to the bottom of whether they're sampling, whether whether they're only sampling the environment once.
By the way, Taka, if you scroll back up to algorithm 1, on the right side, they show you an example of their basically custom reward function. So to the right of where in the given section, a reward function, to the right, they show, for example, minus absolute value of f sub g of s equals 0. What that is f sub g of s
is that absolute value? It looks like it's parentheses.
Oh.
Or like it doesn't
maybe
look like
maybe it's
yeah.
No, you know what it is? So f sub g of s is the set of state is
it's like a negative identity, right? Probably. Like if you're in the goal state, you get 1, and if you're not, you get 0.
Yeah.
But so then my next question is the goal part of the environment? Or does the environment only have one goal?
The environment only may have one goal. You're creating these
other goals.
Yeah, they say that they say very clearly that the environment only transitions in one way. Like that's fixed. And all this other stuff, the additional goals, is all within the algorithm.
Okay. So then that's a lot like reward shaping now.
I think that what I said in the beginning, I still feel that's true, is probably depending on the environment, this might be simpler to apply to some environments, like this robotic environment. Whereas I think for other environments like lunar lander, reward shaping is probably simpler to apply.
Yeah, I can see that. I think that's their motivation too, is that, for example, how do you come up with a reward shaping target for this environment? And I think in 4.3 or 4.4, they consider compared to reward shaping.
Okay.
I think they try to do both at the same time.
Yeah, they do the first, and then they do the second, which is comparing both at the same time.
Let's talk about this stuff because it's interesting. Let's start with 4.3. Does her improve performance even if there's only one goal we care about? So they say that even if there's one goal you care about, simulating other goals will help that single goal. Okay. From figure 4, it is clear that DDPG plus her performs much better than pure DDPG, even if the goal state is identical in all episodes. So this one.
Yeah, and I guess they're focusing on pick and place because that's the actual goal we care about. That's the
Mhm.
single task, right? So in
Yeah.
pick and place, you see a much better behavior, much better result.
So they're saying that in this going back to the algorithm, right here, right here, when you sample a goal for the first figure that we just talked about, figure 3, this is a pure sampling of the goals. So you can end up with either goal 1, 2, or 3. But in figure 4, they don't sample here. They just focus in on a specific goal, and they
Wait, is that what they do?
I have a question. Yeah, but go ahead.
Why wouldn't they just do the same thing? But the goal set is identical in all episodes.
Yeah. So what does so I have a question here. Is this experiment in figure 4? Is it that pick and place is your
Oh, I see.
goal of interest? Is pick and place your goal of interest, and you're seeing how often do you end up being able to push and slide? In other words, how often do you end up in the terminal state for those goals, right? And get that reward. So
no.
if
Figure
I'm reading
4,
it,
goal of interest is each of these things. Like this is for pushing. So this is in that state, we just specify push as the goal. So instead of sampling a goal, we just hone in on push. And then this one is we just hone in on slide. And this one is we just hone in on pick and play.
Oh, in that case, they fail at sliding, right? Because it looks like DDPG outperforms them.
Yeah, I think the variances are weird, but or they're kind of overlapping. But
yeah,
so that's the second interpretation, Taka. The interpretation I was going with, and it's not clear to me right now, as of right now, which one it is, but is if your goal of interest is pick and place, and how often you are able to hit the terminal states of those specific goals, then this figure makes sense to me, meaning you're able to do pick and place, but along the way, if your goal of interest would have been sliding, how often are you able to hit that, right? If you trained for just pick and place. And it makes sense to me that DDPG with count-based exploration and DDPG with her are kind of similar, is because you have to learn one of these tasks first. And for the sliding is on the way, might be on the way to pick and place. So you're going to get equal sample efficiency for that first task because there's no previous goal, right? So it's not going, her is not going to help you. Versus, for example, it seems as though for pushing, it's not as correlated to pick and place.
That makes sense. That makes sense for like yeah. If your goal is to slide, if you can already pick and place, you can already slide, right? Probably.
Right.
So there's like in terms of curriculum learning, looking at it from that angle, it's like it's backwards, right? None of these other tasks really help you with sliding.
Right. So
but I think these figures are what Taka said. I think for each one, you're actually, the goal is whatever is at the top. The title of the graph is the goal.
Okay, so you're training towards that goal only.
That's the only thing. That's the thing that makes most sense if I read this paragraph and read the.
So what is the difference in that scenario between DDPG plus her and DDPG? Because you would only sample the one goal, right?
So if you go back up to the algorithm 1,
yeah,
it's what Taka was saying. That first part, you're only sampling the one goal, but then if you look at the second for loop, you're creating a whole bunch of trajectories for all the goals that you have that you've defined, not just that one goal.
So you're allowing like the 4 samples.
So the only difference is the behavior policy.
Yeah,
right.
Exactly.
The behavior, you're just sampling from that one behavior, whereas when
Okay.
you're sampling from a
Okay.
goal.
When you're training all of them, all the behaviors, all the goals. So the batches that you're actually training on have
Sure. So you're creating experience for each goal, but you're only sampling for one goal. I guess that's the
You're
way
only
sampling for one.
you're only
No.
acting based on one goal.
no,
Okay.
yeah. When
You're
you're
only
behaving
acting.
in the
Sure.
actual environment, you're
That's
only
what
behaving.
that's what I mean by sampling. Sampling from the
Yeah.
policy. Yeah. Okay.
But figure 3, you're acting based on sampled goals as well. For figure 3,
Yeah, that makes sense. Figure 3 makes sense. So figure 4, it's sampling based on pushing in I guess the one on the left, versus on the right, it's pick and place. So okay, let me think about this.
What's the difference
why
between
is-
sliding and pushing? Like in terms of the actual actions?
pushing. In this task, the box is placed on a table in front of the robot, and the task is to move it to the target location. The robot fingers are locked.
Look at figure 2. Figure 2 has a diagram.
Pushing top row, sliding middle row, pick and place bottom row. Sliding. In this task, a puck is placed on a long, slippery table, and the target position is outside of the robot's reach, so that it has to hit the puck with such a force that it slides and then stops.
So it's like hitting the thing. It's like hitting the object and forcing it to
Move.
like move. Yeah.
Yeah.
Versus pushing, which is like continuous force applied.
So sliding seems to be the simplest action, right?
Pushing is simplest, I think. No, because sliding you have to account for like your force. It's
I
like
would think
that
sliding
game,
is even easier because you just have to go whack the object.
So if you accidentally bump into an object, it's going to slide,
Yeah.
right? But to push it, you have to continually move and
Yeah.
but it
with the
has to, you
object.
have to take into account the friction. It's like that sport, the
Curling.
the curling sport. Yeah, it's like pushing something to a place. That's super easy, right? Because you just push it there. But sliding, you have to.
No, but that requires intention. Like if you let's imagine that you're initializing the policy to random neural network, right? It's not going to just push something to a place in the beginning.
Oh, so you're saying sliding, you get
What's it going to do
luckier,
by accident? It's not going to pick
you
and
get
place by
lucky
accident.
It's
better.
gonna slide. Yeah.
It's going to slide.
Yeah.
And I'm just trying to verify Farouk's
Okay.
hypothesis,
Yeah.
which I think is right,
makes
which
sense.
is that the reason DDPG
That
plus
makes sense.
her does not exceed the performance of DDPG alone is because sliding is probably the most fundamental of those three.
It seems like
to get lucky.
It seems like it's easier to get lucky, but it's also harder to solve because if you look at it, the success rate is so low. You have to account for things like what Taka was saying, that it's probably easy to get started with it because you just have to go whack the object, but
you have to have a precise force.
But you have to have a precise force to get it to the location. So if that's your goal of interest, it's a hard task.
And none of the other tests help you. Like picking and placing does not help you learn how to hit something with the right force, right?
Yeah.
So this now ties in well with what I was saying before. Remember how I was saying that there's some environments like Lunar Lander where I feel like it will require an extreme amount of domain knowledge to design good tasks? This is kind of proving it. Because if your task is sliding, pick and place and pushing are just not enough, as you can see. This kind of proves what I said. I think if you wanted this agent to do well at sliding, you'd have to come up with some very complicated tasks, like for instance, moving at a fast speed.
Yeah.
Because you need to move at that speed in order to hit the block with that speed.
So actually, based off this, is picking and placing is the easiest task, right?
Easiest task with this architecture, with a goal-oriented RL architecture, it's the easiest task to master. Because
even not with goal-oriented, based off the data we're looking at right now.
I don't know if we can say that.
if you just use count
Oh,
based
I
exploration.
I guess because that curve is at 60%.
Yeah. That's huge variance though. But
Yeah, I wonder how many times they ran it.
I
It's
think
like
they said 5
it
times.
spans the whole graph.
Yeah, I think
The
they
whole
said
Y
5
range.
times. 5 times.
I like that though. I like that they're showing the true error bars, but
They might as well color the whole chart green. It's like
no, but it's
Yeah,
interesting how narrow the bars are for all the other lines, but just for that one, it's like, I mean, I guess that means that it completely failed one time and it completely succeeded like half the time. You know what I mean?
yeah. All right, section 4.4. How does this relate to reward shaping? So figure 5 shows the results. Oh, so they mixed in reward shaping with this goal-based thing is section 4.4.
Yes.
Right. So this thing is the shaped reward, basically.
Yeah, I think doing reward shaping on its own would not maybe be a good ablation because we could always say, hey, your reward shaping functions aren't good.
Okay, so this
You
is
know what I
not
mean?
comparing. This is like
Yeah.
combining.
I think you could always claim that, but how else can you show that? How else can you show that this is better than, or this is an alternative to reward shaping?
It's like it's almost like a conflict of interest. Like their paper is on HER. Like if they're going to design some reward functions that don't work as well, why would we buy that? You know, why not? You know, unless they're picking the reward functions like well-known reward functions for this task if they're already published.
Okay.
And in which case they might work, right? If they're well known. See what I'm saying, Farouk?
No, I see what you're saying. There's a conflict of interest in the fact that
If you were to do that ablation with your own like made up reward functions, it's like, how do you convince someone that no reward function works? It's impossible to do in a paper, right? You can only convince
so
people
they
that
actually
your
do
reward
both.
functions.
So they do both. So in figure 5, DDPG is, you know, with the reward shaping.
With
DDPG
those reward
plays,
shaping. Yeah.
Yeah. And they pick a certain type of reward. You could see that it's like based on some lambda. I don't know. Okay, so it's based on the goal, based on the state of the object, or perhaps the position of the object. That's the difference of.
But if it's not working with her, it makes sense that it probably wouldn't work with DPG either.
Yeah.
But imagine you had a reward shaping function that did work with DPG. Would that work with her? Maybe not for this task, but for some other task, right? Because there are clearly environments where word shaping works, right? Word shaping is a very commonly used tool, right?
I guess one other thing they're careful about is they call this domain agnostic reward shaping. Because they said that for every problem, there exists a reward which makes it easy. So basically they're saying that if you don't have, apparently it's the original reward shaping paper, by the way, from 99, the Andrew Ng one.
Potential based, yeah.
Yeah, potential
Very
based.
nice.
So I guess supposedly for every problem you can find some, or for lots of problems, I guess you can find some domain specific reward shaping that can make it.
But you know, that's kind of the point, is that humans have domain knowledge. And if you really care about getting a project to work, you're going to use all the domain knowledge you can muster, right? You're not going to just use some domain agnostic reward shaping because you're principled, right? You're going to use anything you can do that's going to work the best that you know how, right?
I think that's true when you're trying to do this in a practical setting, but in a research setting, you want things to be as general as possible, right? So from a research setting, I think it makes sense to compare to this domain agnostic thing.
I know what you're saying. I don't know if I agree though, because their goal definitions require some domain knowledge. So is it really fair?
So I think in this case, some of the stuff we were talking about the correlation, some of that actually, if you look at the results, partially exists, but partially doesn't exist. Because if you look at like in that individual figure 4, it almost seems like these might even be multiple different tasks. Because just for pushing, it doesn't look like it, it improves it a little bit. But for sliding, it doesn't improve it at all. So it seems like some of the other tasks, doing well with sliding is hard enough that being able to, adding those extra experiences doesn't seem to help. Versus for pushing, it does seem to help, at least a little bit. And for pick and place, it does seem to help. So I guess like I can see that there's something slightly unsatisfying about not comparing this to the best reward shaping you could possibly do, which it does. I mean, it doesn't seem like they've done, but I still think it's like valuable.
Well, the best reward shaping you can possibly do, I think they talk about it in the Ing paper, is the value function. Right. So if you do that, it's kind of cheating.
But you don't know that, so no,
you can't do that.
That's like the ultimate form of domain knowledge.
Yeah.
Right. Like,
but I'm not even saying that. I'm just saying, find an environment where there's good, like a complex environment that has reward functions that work well, and on that environment do goal oriented RL, and then do a comparison.
Sure. Yep.
I mean,
I can see that.
It's kind of more of an art than a science, because you can always quibble and say, hey, this reward function is too good, or but I mean,
I do think at a base level, this is kind of I think HER seems like it's a form of reward shaping in itself.
Yeah,
I mean, we go back there. Yeah. Yes, it does.
We've come full circle.
Especially if the goals are self-defined. I think, yes, then it becomes a lot like,
defined by the engineer?
Defined by the engineer, the agent, the researcher.
But it does feel like it's something that might require less for most things. For most like things I can think about, it might require less domain knowledge than than reward shaping. Because you're taking with rewards shaping, you're taking something that's sparse and you're using a function or some potential based thing or some function to make it dense. Versus with HER, where you're making it less, it's still sparse. You're just making it a little bit less sparse by creating these terminal states, that these goals or these other subterminal states that end up giving you some reward.
Right? I understand what you're saying. I personally, the way I'm thinking about it is, some environments are maybe more naturally suited to one versus the other.
They might be, for sure.
And then maybe deep down underneath, there's some unifying theme between the two. I wouldn't be surprised.
I think one other interesting thing about HER is this fact that because you have these sub-defined goals, you're actually able to produce more episodes, or produce more experience for a single transition.
I agree.
For a single transition.
I mean, that's where it gets all its power.
Right. So I think that part is the difference between actual reward shaping. But the fact that you have this reward function that you're like kind of superimposing over the environment, that is reward shaping.
I have to say, reward shaping adds density too, and it makes learning more sample efficient as well, because
it does.
When you have sparse rewards, you're not learning most of the time when you don't get a reward.
But
You're not really
but
doing
with
much learning.
reward shaping, you're using like some explicit domain knowledge to come up with a function to make things like very dense. You can make things really dense with
Sure.
reward shaping, right? Typically, you do actually, most of the time, right? Because it's like it's like distance to the goal or something, right? You know, so at every time step, you're getting this, you're getting a dense signal, versus with her, you're getting a slightly less sparse signal, right? But instead of having to define a function, you're defining goals.
You
So,
know,
yeah,
I want to step back 1 second, because one
Yeah.
thing they said that I liked, they said that, and this is kind of a lot of people in doing AI research kind of keep this in their mind when they're trying to figure out new algorithms. When a human learns, like when we learn, we're very sample efficient, in the sense that, like, let's say you want to go, you have some task you want to do, even if you fail, you learn a ton along the way, even about the original task, right?
Yeah.
It's like failing sometimes teaches us more than actually succeeding, right? And you know, with that, back to that hockey example here, if you shoot the puck and you miss 5 feet to the left, you immediately know that all you have to do is aim 5 feet to the right and you're going to score next time, right? So you actually like pretty much learn how to score even though you missed, right? And the one thing I like about this is this seems to kind of be very similar to how a human learns, in that we kind of take quote unquote mistaken trajectories and turn them into, you know, positive trajectories, right? When we learn, right? And I think that a lot of people doing machine learning now, they're a little bit sad that these algorithms are so inefficient compared to humans, right? And the question is always, how do we close the gap between human brains sample efficiency and machine learning, current state-of-the-art machine learning sample efficiency, where you need, like, you know, you need to play billions of games of chess to get to like a 2500 elo, whereas a human can play like 1,000 games and get to a 2500 elo, right? Clearly we're doing a lot more sample efficient learning in our brains, right? So from that standpoint, I just at a very high level, I think this is kind of a cool framework, because it kind of
I
mimics
agree.
mimics the way a human learns a little bit.
Yeah.
There is a spectrum of goals that you can define that is going to be like helpful to this algorithm or make it outright not converge. I feel like I was thinking, what if you devise a goal that's an exact opposite of the actual goal?
But Farouk was saying that you might still learn from that because it's
Yeah.
so anti-correlated, right?
Yeah.
You learn what not to do.
No, that rewards you for, like, let's say you come up with a goal that is like, with a hockey example, like -1 for scoring, and then
Oh, that's
I don't
that's
know, 1
bad.
for everything else.
That's bad, because you're taking the same task. So you have one goal where it's a +1 for scoring, and now you're creating a new goal which is -1 for scoring.
Yeah.
That, I believe, would be terrible.
Right? So that there is some continuum of like good goal versus bad goal. Same as reward shaping. Like there's a continuum of good.
Okay, you know what it is?
Versus bad
A key premise here is that all the rewards are binary sparse. So they're all +-1. There's no, I mean, sorry, +1 or 0. There's no -1s.
Right.
So
see if you can come up with an example like you just did, but for the case where you can only assign +1s and 0s.
So 0.
I'm not saying it's not possible, but
0 for goal and then 1 for everything.
1 for missing.
one for
Yeah,
everything.
that might do it.
wait, so
I
you're
don't know
saying
if you call
that if you had
sparse.
another task?
It's
No, that's not
inverse
sparse, is it?
Inverse sparse.
Well,
Wait,
yeah, because
so, okay, so I'm trying to understand Taka's question. So Taka, you're saying that what if you created a task that was kind of a distractor variable, or like a distractor reward, where
Yeah. Or like scoring on your own goal. How's that?
the thing is, scoring on your own goal might teach you how to score, which is useful in scoring on the enemy goal.
no, okay, here's the this is
Right?
where Taka,
Yeah.
this is where the loophole might be.
Yeah.
Remember that we're conditioning on the goal. So yes, if you assign 0 for scoring a goal and 1 for everything else, that seems like it's bad. But the thing is, you're inputting into the neural network this new
Correct.
G sub 3. So the network knows that this is a
Correct.
completely different goal. And
Yeah.
I actually think that it'd still be fine.
Yeah, it might require more samples. It might require. It might require if that task at best was completely random, right? Had completely random correlation. It might just require like more samples. Look at the figure for sliding. In that case, it was no better. Actually, no, the one where they look at just sliding. Yeah, figure 4. It's not better, but it doesn't hurt.
Taka, I actually have an answer to this, a precise answer to this. When you enter, so imagine your neural network has all the features of the environment plus this G, the goal, right? When we enter the goal where it's +1 to score, the coefficient on all the parameters would be +1, plus some whatever the current coefficient is. When you now make the goal 0 for scoring, just flip it to minus. You don't even have to change the parameters because it's like the opposite task, right? So basically, whatever the weights were, if you just flip their sign, you actually get, you do well at this new task, at this new goal. So this G would just be like a -1 to all the multiplied by all the parameters. I think we're still okay.
Yeah, I think overall it's not gonna hurt.
Hey, one more thing before we wrap up. I know we're running short on time. Taka, if you scroll down to figure 7, I thought this was cool. They actually tested this on a real robot, and it kind of failed the first time. They tested the pick and place policy, and it was only succeeded 1 out of 5 times the first time, and they realized it's because there's sensor errors in a real robot, right? As opposed to like perfect state information in a simulation. So they redid their simulation with Gaussian noise on the state observations, and then they got like perfect performance on the actual robot.
Cool. All right. I think we've deciphered this paper for 90 minutes. Pretty good stopping point. With this episode, I want to start doing each one of our kind of summary / takeaway / something new that we learned. I'll go first. So what I thought was interesting, actually what I learned from today's discussion is the surprisingly closeness of goal condition reinforcement learning with reward shaping, and the fact that these goals are not necessarily defined by the environment. Us as researchers / agents / practitioners can also come up with our own arbitrary goals. And I guess I'm convinced that no matter how random or how poisonous that goal might seem, the agent will be able to learn something from it. At least worth experimenting. I think it's an interesting idea. That's my takeaway. Who wants to go next?
I'll go next. I think I just got a much better grasp of how this algorithm works, listening to all the back and forth. But I was struck by the one thing that I was just saying about how we're striving to make these algorithms more sample efficient. And I think that this is probably the one takeaway from this algorithm is the like almost exponential growth in experiences due to having multiple goals. Like, 5 goals, we get 5 times the number of experiences, 20 goals, 20 times the number of experiences. And we can kind of learn off of almost anything that our agent does. Although I think this probably works better in some environments more than others.
All right, Farouk.
All right, and so I guess just to echo off what you guys have said, I mean, in terms of sample efficiency, I think this is, I think that was the biggest takeaway for me is that the ability to, with a little bit of domain knowledge, if we're able to come up with some of these goal states, we can first of all generate more data and make use of that data to solve these problems in a more sample efficient way. So that's, I think, kind of the main takeaway. But I think one other interesting thing is this notion of kind of multitask. If you have these multiple tasks, typically with a lot of RL, at least a lot of the RL papers I've read, or the practical things I've seen, they're very like unitask. You're playing Go or playing StarCraft or Gran Turismo racing or poker, but in a more general setting in terms of how humans learn and how many agents or animals or things like that learn tasks. That there's many tasks that are kind of either correlated, anti-correlated, kind of random, and how doing this type of multitask, multi-goal training improves sample efficiency. So I think that's like a really interesting thing, and building these types of curriculums in terms of tasks, right? I think that was kind of I think really like the interesting part about this paper, and of course, the ability to go from very sparse rewards to slightly less sparse rewards as well.
Learning from failure. Great. I think those are great takeaways. And our time is up for today. Really interesting discussion, guys. Listeners and watchers, if you like this, please follow us on Twitter. We have a Twitter account, ArgMaxFM. Subscribe to our podcast, subscribe to our YouTube channel. And we're always looking for feedback. So if you want to provide us feedback, you can either tweet at us or comment on YouTube, or get in touch with any three of the co-hosts. We love to hear from our listeners. But with that, thanks all, and see you next time. Bye-bye.
Bye.
Bye.